This videotape, the second in our series on geometry, deals with triangles. Triangle is a closed three-sided figure. Certain types of triangles come up very often, and we're going to give them special names. An isosceles triangle is one in which two of the sides have the same length. Okay, this is an isosceles triangle. This is the symbol for triangle. Okay, we call this the base of the triangle because it's resting on this side. These two sides have the same length. If in a triangle all three sides have the same length, such a triangle will be called an equilateral triangle. This symbol means that all the sides have the same length. Here only two sides have the same length. This is an equilateral triangle. You could also say that this triangle is isosceles since it has two sides equal. We mean this in the sense at least two sides equal in length. Okay, so this is also an isosceles triangle, but we would like to use the most descriptive term, okay, for any particular figure. So we will call this one equilateral because it has three sides equal. This one only has two sides equal. We will call it isosceles. Any triangle that has a right angle in it is called a right triangle. A right triangle. Okay, now you can have an isosceles right triangle in which two sides have the same length. This side has the same length, and there is a right angle in it. This would be an isosceles right triangle. Okay, by the way, the side opposite the right angle in a right triangle is called the hypotenuse. This is the hypotenuse of the right triangle. And the other two sides in a right triangle are known as the legs of the right triangle. Okay, now while you can have an isosceles right triangle, you cannot have an equilateral right triangle. This is a consequence of the fact that we have a theorem that says the sum of the angles in a triangle is 180 degrees. The sum of the angles in a triangle, in any triangle, is 180 degrees. Now I'm going to prove this theorem for you. Okay, we also have another relationship that says that in an isosceles triangle, okay, not only are these two sides equal, but these two angles are also equal in length. This is really a theorem. We're not going to prove this one. I'll write this down for you in a moment. Okay, the point I'm trying to bring home here is that if the sum of the angles of a triangle, 180 degrees, okay, and a right angle, of course, is 90 degrees, well, it's very simple to see that you cannot have an equilateral right triangle. You cannot have 90, 90, and 90. You have to have at least a right angle in it. Okay, it has to be a right angle, or it wouldn't be a right triangle. An equilateral right triangle would mean three right angles in it, and that would not give us a triangle, because we'd have a sum of 270 degrees instead of 180 degrees. But it is quite possible to have an isosceles right triangle. Now, as I said, in an isosceles triangle, the two base angles are also equal. So if this angle is 90 degrees, and the sum of the angles in a triangle 180 degrees, that means we have 90 degrees to split evenly between these two angles. This angle would be 45 degrees. This would also be 45 degrees. All isosceles right triangles, okay, have 45-degree angle, a 45-degree angle, and a 90-degree angle. You cannot have an equilateral right triangle, but you can have an isosceles right triangle. It's a special type of right triangle. Now let me prove this theorem for you, that the sum of the angles of a triangle is 180 degrees. What makes this theorem interesting is the fact that we construct a line in proving the theorem. We put in a line that wasn't there originally, and this helps us to prove the theorem. It is okay in the proof of the theorem to put in a line that wasn't there originally if such a line can be constructed using a straight edge and a compass. Now let me go through the proof. We have a triangle, any old triangle. We don't want to make it anything special. And I would like to have at least a horizontal base here. Through the vertex here, I want you to construct a line parallel to the base. Okay, this is a legitimate construction. You are allowed to do that. We have a triangle in here. We want to construct a line parallel to the base. Now, just to make this a very simple thing, a simple proof, let me just label the angles. Let's label this angle 1, angle 2, angle 3, angle 4, and angle 5. Angle 4 runs from here to here, angle 2 from here to here, angle 5 from there to there. This is angle 1 and angle 3. And the line constructed is parallel here to the base. If we extend the base, these two lines are parallel. Okay, now we're trying to prove that the sum of the angles in a triangle, any triangle, is 180 degrees. We start by saying that angle 4 plus angle 2 plus angle 5, they sum to 180 degrees. This is true because angle 4, 2, and 5 together form a straight angle, one which has degree measure 180 degrees. 4 plus 2 plus 5 together gives us, those angles add up to 180 degrees. Okay, now we also have parallel lines in here. We have the dotted line and the base here. These are parallel. And think of this line here as being a transversal. So two parallel lines being cut by a transversal. Two parallel lines cut by a transversal. The alternate interior angles are equal, which means that angle 4 equals angle 1. These are alternate interior angles. Similarly, if you think of this side of the triangle as being a transversal for these parallel lines being cut by this transversal form angles 5 and 3 are alternate interior angles. So angle 5 is equal to angle 3. Okay, angles 4, 2, and 5 together added to 180 degrees. Angle 4 was equal to angle 1, alternate interior angles. Notice the Z shape that we mentioned in an earlier videotape. Angles 1 and 4 are the alternate interior angles. Angle 3 is equal to angle 5. Now, by substitution into the original formula over here, if angle 4 is equal to angle 1, when we see angle 4, we can replace it by angle 1. Similarly, if angle 5 is equal to angle 3, we can replace angle 5 by angle 3. Doing that, this top line becomes, instead of angle 4, I write angle 1. Now I'll leave angle 2 alone. Okay, and then angle 5 is equal to angle 3, so I replace it by angle 3, and I get, by substitution, that angles 1, 2, and 3 add up to 180 degrees, and of course these are just the angles of the interior angles of this triangle. There was nothing special about this particular triangle in our proof. Okay, so we have shown that the sum of the angles of any triangle, they add up to 180 degrees. And knowing that, we know, for example, that we cannot have, I mentioned before, an equilateral right triangle. You can't have three 90-degree angles. You can't even have two 90-degree angles in a triangle. You can't have two 90s and a 0. Okay, this tells me right away that the largest an angle can, well, let's leave that alone. Now, we have other theorems that are going to be important to us. As I mentioned before, an isosceles triangle is one that has two sides with the same length. There is a theorem that says that if you have an isosceles triangle, the base angles are also equal. And not only is this theorem true, but the converse is also true. That is, if you have a triangle in which two of the angles are equal, then this triangle also has two sides equal in length. In fact, it's the two sides that are opposite the two angles, and it's an isosceles triangle. Okay, we can write down this theorem. A triangle is isosceles if and only if the base angles are equal. Okay, this if and only if business is a way of saying that not only is the statement true, but also its converse. That is, if a triangle is isosceles, then the base angles are equal. I mentioned that before. And also, if the base angles are equal in a triangle, then the triangle is isosceles. This is a theorem and its converse. They're both true, and we specify that by the if and only if. Okay? Ordinarily, in other words, if you see a theorem written out without this, you assume that it's only true in the way it's stated. It is not true that all statements and their converses are true. For example, if I say, you can make the statement, if you are President of the United States, then you must be born in the United States. Okay, that's the rule. To be President of the United States, you have to be born in the United States. You cannot then say, well, if you are born in the United States, then you will certainly be President of the United States. That does not work out. Okay, so you see an example. A statement is true, but its converse is not true. But in this particular instance, okay, this, the original statement of the theorem and also its converse are both true. Now, one more thing I want to mention about triangles, and that is, in general, the largest angle lies opposite the largest side. The smallest angle lies opposite the smallest side. The middle angle opposite the middle side. If we look at this triangle, say here, this is the longest side in the triangle, the hypotenuse, and this is the largest angle. Okay? Obviously, it has to be, well, you can see it from the diagram, but if this is 90 degrees, the other two angles have to split 90 degrees between them. So obviously, neither one of them can be as large as that. The longest side opposite the biggest angle. And from the diagram, it appears that this is the next largest angle, this is the smallest. And notice that smallest angle, okay, opposite is the smallest side, the middle angle, and opposite is the side that has the in-between length. This is the smallest, the middle, the largest length. Okay, so in general, the greater angle will be opposite the greatest side, and so on. By the way, by following this through in an equilateral triangle, okay, since all the sides have the same length, all the angles are going to be the same as well. And since you know that the angles in a triangle must add up to 180 degrees, you have 180 degrees to be split evenly, okay, among these three angles. They must, therefore, each one must be 60 degrees. 60 degrees, 60, 60. All sides the same length, all angles are going to have the same size. 180 degrees, the angle sum of a triangle to be split evenly among the three angles, each one will be 60. Okay, now to make sure you understand the ideas that we've introduced in this tape, and also we're going to we'll use some of the ideas from the previous tape on parallel lines. I want to give you some triangles, and I would like you to fill in the missing angles and the missing sides where I indicate them. In the first example, let's consider this triangle. Let me tell you that, let's call this triangle ABC. Angle A, let's see, angle B we'll say is 80 degrees. Angle C, 35 degrees. And I'm asking you, what is angle A? Okay, this is the first example. And here we make use of the fact that some of the angles of a triangle has to be 180. So angle A plus angle B plus angle C is 180 degrees. Angle A plus 80 degrees plus angle C, which is 35 degrees, must be 180 degrees. This gives us angle A plus 115 degrees is equal to 180 degrees. And subtracting 115 degrees from both sides, we see that angle A must be 65 degrees. 65 and 115 gives us the 180 here. This is 65. 65 and 35 gives us 100, and 80, 180. The angles add up to 180 degrees. Okay, let's consider another example. Triangle ABC. This side, AC, has length 10. AB has length 7. I will tell you that this angle is 100 degrees, angle B, and angle A is 40 degrees. And here I am interested in angle C and the length of BC. Here are the things we're trying to find out. Okay, since angle A, once again, angle B, and angle C must add up to 180 degrees, and I already know that A and B are 40 and 100, this tells me that angle C, this is 140 degrees, plus angle C is 180, angle C must be 40 degrees. Of course, you can figure this out without all this extra work. Angle C here must be 40 degrees. So 40 and 40, 80 and 100, 180 for the triangle. Now, having seen that, we notice that this is an isosceles triangle because the base angles are equal. Okay, if it's an isosceles triangle, then two sides have the same length, and of course those are going to be the two sides that are opposite the base angles. So if the side here, AB, opposite the 40-degree angle is 7, then this side, which is also opposite a 40-degree angle, has length 7. So angle C is 40 degrees, and the length of BC is 7 units. Now let's consider an isosceles right triangle. Okay, with a right angle here at B. And these two legs have the same length. Let's say that this is 6 and this is 6. And I'm interested here in angle A and angle C. Okay, I'm not going to ask you for the length of AC. You'll learn how to do that in I think the next videotape or the one after that, but right now we're going to concentrate just on angles A and C. There will be a method, okay, for figuring out the length of AC. There is a videotape on what we call the Pythagorean theorem. That'll come a little later. Right now, all I want from you is the lengths of the sides of angle A and angle C. Okay, now we know that angles A, B, and C, of course, must add up to 180 degrees. At first glance, it might not look like we have enough information, but we have something extra here. We know it's an isosceles right triangle. Two sides are equal, therefore these angles must also be equal. Angle A must equal angle C. Let's say they're both equal to x. Then angle A plus angle B plus angle C must be equal to 180 degrees. Angle A, we're saying, is x. Angle B is 90 degrees. Angle C is also x. So 2x plus 90 degrees gives you 180 degrees. Subtracting 90 degrees from both sides, 2x is equal to 90 degrees. Dividing both sides by 2, x is 45 degrees. Okay, so angle A is equal to 45 degrees, and angle C is also equal to 45 degrees. Of course, you could do most of this in your head. You simply say, it's an isosceles right triangle. These two angles are therefore equal. They're like the base angles. Of course, I mean, the triangle is not lying on its base, but I mean the two angles that are opposite the two equal sides. These two angles are equal. Since this is 90 degrees, that leaves 90 degrees to be split evenly between those two, 45 and 45. Okay, what I'm going to do is put one triangle on top of another one. I will assume that this is a right angle, this is a right angle. Okay? You can think of this as a vertical line and these two as being horizontal. Regardless, we have these two sides as parallel. Okay, it wouldn't matter if the whole picture was tilted. The horizontal and vertical is not important here. What is important is that this is a right angle, this is a right angle, and what we have here is a setup. We have two lines being cut by a transversal, and we have the alternate interior angles equal, therefore these lines must be parallel. Okay, let's call this A, B, C, D, and E. And all I'm going to tell you here is that angle A is 25 degrees, and I want you to figure out all the unmarked angles. Okay, the first angle we'll work with is angle ACB. We have to figure out ACB, which is this one here. Saying angle C is not clear because we have two angles here involved. Then I also want angle DCE and angle CED. Those are the ones I want you to find. Okay. Now let's work with the upper triangle here. You know the sum of the angles of any triangle, 180 degrees. And we have in this triangle, this is a right angle, this is 90 degrees, and this is 25. 90 and 25, that gives us 115. This tells me that what's left here, this must be 65 degrees. 25 and 65 gives us where are we? 25 and 65, that gives us 90 and 90, 180 degrees. Okay, so angle ACB, that's 65 degrees. Sum of the angles in this triangle must be 180 degrees. We had 25 and 90. That left us with 65 for that angle. Now, the next angle, angle DCE, must also be 65 degrees. Why? Because what we have here are two straight lines intersecting and forming vertical angles, the opposite angles. Here are the vertical angles, and we already know from an earlier tape that the vertical angles are equal. Okay, so this is also 65 degrees. And if this is 65 degrees and this is 90 degrees, this must also be 25 degrees. Since we have the bottom triangle, the angles in the bottom triangle must add up to 180 degrees. 65 and 90, leaving us with 25 degrees for this angle here. Now, there are other ways of getting these same answers. You could have found, say, well, you have the 25 and the 90 degrees, so we knew the 65. You could then make use of the fact that if these are parallel lines, think of this as a transversal. We have here alternate interior angles. This is 25. This must also be 25, so we could have gotten that one. And then 25 and 90 leaves you with 65. But, of course, these two are equal from the vertical angles. So there are various ways to get the same information. The interesting thing here is that the angles in this triangle are equal to the angles, are respectively equal to the angles in the bottom triangle. This triangle here has angle 25, 65, and 90, and this one also 25, 65, and 90. Okay, these triangles are said to be similar. They are triangles with the same shape, not necessarily the same size. Okay, these don't have the same size. This is like a blown-up version of this one. Two triangles that have the same shape are called similar. Similar. Similar, here we have similar triangles. Okay, that means they have the same shape, not necessarily the same size. And in triangles, it means that each angle in one is equal to, every angle in one triangle is respectively equal to an angle in the other triangle. 25, 25, 65, 65, 90, and 90. Obviously, you can get by with two angles in one equal to two angles in the other. Since all the angles must add up to 180, the third must also be equal. Now, similar triangles have just the same shape. As I mentioned before, these two triangles, for example, if they have like the same shape, these are similar, assuming that the angles are the same. Okay, if triangles have not only the same shape, but also the same size as well, we call them congruent. Okay, congruent triangles. I'm asking you to believe that these not only have the same shape, they're similar. In other words, this angle is equal to this angle is equal to this angle is equal to that. Not only similar, but also exactly, not only the same size, the same shape, but also the same size. As you were to cut this one out and superimpose it on this, it would exactly cover it up. These are identical, okay, like stamped out by a cookie cutter. These have not only the same